Welcome to the solutions to the Regents Physics Statics problem set, problems 3 and 4. Problem 3, if you are pushing a lawnmower across the grass, can you increase the horizontal component of the force? That would be the Fx component. You exert on the mower without increasing the magnitude of the force you apply, and explain. What we're going to do on this diagram of this man pushing the mower is draw the force directed along the handle and talk about the two things that that force does from a component standpoint. One is that this force with the vertical Y component pushes down on the mower. Well, really, this is a wasted component because the mower doesn't need any help being pushed against the ground. It's already pulled against the ground by the force due to gravity. Nonetheless, that vertical component, that is what it's doing, is it's pushing down the mower down against the ground. The other component is the usefulness out of our force. This, of course, would be the X component, which is what causes the mower to move across the ground itself. And of course, between the force itself and that X component and the horizontal is the angle theta at which the force is applied along the handle. Let's refocus on the question being asked here. Can you increase the horizontal component of the force you exert on the mower without increasing the magnitude of the force you apply? So what they're saying is, is it possible to increase Fx without increasing F itself? The answer is yes, if you take the force along the handle and simply lower the handle, or in other words, decrease the angle. So, if we were to write the relationship between Fx, theta, the angle, and the force along the handle itself, on the reference table we find Ax equals A cosine theta. And if we look over, A stands for any vector quantity, so it becomes, in this problem, Fx equals F cosine. Whoop, sorry about that. F cosine theta. And if we're analyzing the situation here, they don't want us to change the force. They want us to increase the horizontal component. And the way to do that is to decrease the angle so that overall the cosine of theta goes up. Okay? And if you do some calculations on your calculator, you'll see that that's the relationship among the variables there. Okay, so there's your answer and the explanation for it. For number 4, we have the transmitting tower of a TV station held upright by guy wires that extend from the top of the tower to the ground. The force along the guy wires, tension, can be resolved into two perpendicular components. All right, let's start there before we look at A, B, and C. Here's a picture of a transmitting tower for a TV station. And here are the guy wires. They would actually be going off in several directions to help stabilize the tower itself. And any time we have a force in a cable, a string, or a rope, we call that force tension. And of course, this is the angle theta with the ground itself. What this is saying is the force along the guy wires can be resolved into two perpendicular components. This tension does two things. The vertical component of the tension pulls the tower It pulls the tower down toward the ground. The horizontal component, the X component, would pull the tower away from where it's located. Obviously, the idea here is that you set enough of these up where the X components cancel each other out. And here's the Y component from the other cable. So we're looking for the X components to cancel each other out and keep the tower upright, keep it stabilized. Okay. Now again, we're going to point out in this question that our two TY components in this diagram really don't serve a useful purpose here, because they're pulling the tower down toward the ground, and the tower probably doesn't need any help being pulled toward the ground, since the force due to gravity pulls the tower toward the ground itself. But what is the useful component here in the tension is the X component, which, counteracting with the other X components and the other wires, does keep the tower in place, and that's the usefulness of doing this. Now let's take a look at our questions A, B, and C. If the angle between the wires and the ground is less than 45 degrees, which component is larger? I will do this in red. So let's draw a cable in which it's obvious to us that the angle is less than 45 degrees of the ground. How about that one right there? Okay, so this is less than 45 degrees. Clearly what you see here is that the X component Tx would be much larger than the Y component. Okay? All right, so there's your answer for A. We'll put that over here in red. The Tx component is larger. I'll do the answer to B in blue. And then in B, we have that the angle between the wires and the ground is exactly 45 degrees. Let's try to draw that just as best we can. Okay, and so this angle is exactly 45 degrees. Which component is larger? And so if you know your 45, 45, 90 triangle well, you would understand here that the X component and the Y component at this spot, at this location, are equal. So neither Tx or Ty is larger because they are equal. Tx equals Ty. Lastly, we'll do the answer to C in green. Color code it here for you. And the C asks if the angle between the wires and the ground is more than 45 degrees, which component is larger? We'll make this obvious with this wire right here. And this angle is greater than 45 degrees. And so in this one, that would be the X component, and the Y component would still be the same length as it is shown in the black diagram. Here it should be obvious that the Y component is the component that's larger. Now, what we've done to answer A, B, and C is implored the use of common sense. You could have done all of these analysis by comparing Tx equals T cosine theta and Ty equals T sine theta as given on the reference table, with the Ax equals A cosine theta and Ay equals A sine theta formulas that are on there and just replacing the A with a T. You could have analyzed each situation here, A, B, and C, mathematically, substituting in random values for theta, and just use a standard value for the tension, say 100 would make it easy. So you could see the comparison of the X and Y components, okay? So you could have done a mathematical analysis. We chose a common sense approach and kind of looking at the diagram and being obvious to be able to tell us there. All right, that'll do it for problems 3 and 4. We'll work on problems 5 and 6 in class tomorrow.